had a couple of announcements to make. The first is next Thursday we'll be meeting again, but this time around it will be
This Thursday.
this Thursday. Did I say next? Yeah, this Thursday. We'll be meeting at UNLV, and the directions and the location for the event are on the meetup website, so you can just go there and check it out. I guess parking is free, so you don't need to worry about parking. But since it's going to be our first event at UNLV, we'll assess and see how it goes, whether it's easier for you guys to get there, and what the parking is like, and also get into the facilities in there at UNLV. And then the other thing I wanted to say is that we've started a blog for our group and several other data analysis groups in Vegas. R is obviously there, and then there are others as well, including the Python data science crew. I don't know whether some of you have been there. I have, or you have. Yeah. So Python data science. There is a new meetup group, data visualization. It's yet to have their first meetup, but as soon as they do, we'll have content for them up here on the blog. And then the other is Data Science LV. And so the purpose of the blog is just to post all our content, videos, slides, just like this meetup today is being taped. And so we'll have the video up there if Tom doesn't mind. You know, so we'll have the video up there, and we'll have code,
Just pull the hat down.
slides.
No pressure.
Yeah. So we'll have it all up here. And also the other, probably second major objective is so we can engage data scientists in Vegas in an open and active discussion. I know a lot of you are doing cool and fantastic stuff at your jobs, or even outside of work, and we would like you to share some of the stuff that you're doing, on this blog here. So we invite you to contribute to some articles. I know Steve has been, working on some crazy stuff. Share it with us. So here's a nice blog. Go up there and post something so we could learn from you. And well, as usual, we're supposed to. Well, so you can, the URL is DataScience.vegas, very easy. So just go up there, check it out, and if you have some ideas on what can be done, you can just go to the Get Involved page here, and suggest some ideas on how to better run our group. We want to make it better, interactive for everybody. Just like a couple of weeks ago, I received some feedback from a few individuals, and we're taking that feedback to heart, and we're trying to make the group even much better. And so you can, send some ideas and suggestions. And obviously, I have to mention that some of our sponsors include the following: UNLV for hosting some of our events, Revolution Analytics, recently acquired by Microsoft, O'Reilly, our studio, Work in Progress. That's where the Data Science Python group has their meetups, Innovation Center where we are right now, and Accelerate. And so, yeah, so those are the announcements that I had. And so it's my honor to invite Tom, Vice President of how do you pronounce it? Is it H2O? Or?
H2O, yeah.
Oh, okay.
Just like water.
Like water.
Like water.
That's an interesting name for the data analytics platform. All right, H2O. Vice President, and he'll tell us more about machine learning using this math-intensive platform.
Yeah, thank you.
Thanks, Tom.
Thanks everybody for coming tonight. I'm going to assume that probably most of you have not really had much exposure to H2O, because I believe this is the first time that anybody's really spoken to you guys about it. It's a new, Daniel was just telling me the whole group itself is only about 6 months old, brand new group. So I'm going to just assume that we're all kind of starting from a beginning level. I'm going to talk about some of the things that H2O can do, talk about some of the math that we do, show some of the algorithms, show how H2O and R work together, and talk about things like that. Please, questions, interrupt me anytime. Groups this size are great for getting a dialogue going, so by all means, feel free to interrupt me. Maybe I'll start by just kind of pointing out this interesting little graphic on the right. Anybody have ideas about what that might be?
Streaming data.
Sorry?
Streaming data.
Streaming data. You know, indirectly, yeah, that seems quite possible.
If I clap my hands, will one of the bars go?
I don't know if the sensors go all the way into the guts of my, VPN into my data center, but maybe you can try over in the other room. So this is actually a cluster of 4 machines, and each of these, boxes, each of these rectangles is one host, and you can see the hosts are actually 187, 188, 189, and 190. Those are the last octet of the host. And this is an H2O cluster. So what I've done is I've started an H2O cluster in my data center. Each of these blue bars, anybody have a guess as to what the blue bars represent? Just out of curiosity.
Maybe memory or processor capability.
Those are the 3 best choices: processor, memory, and network. And actually, the winner is processor. So each of those blue bars represents one CPU in one machine. And so this machine's got 32 CPUs, this one's got 32, and so forth. And part of today's discussion is going to be me showing you how from R I can actually drive all of these to be active. And so that's kind of one of the interesting things about H2O. It's a clustered, distributed environment for doing machine learning. And machine learning is very resource intensive, right? CPUs, memory, it wants it all. And so I'm going to show you how we can do some of that driven by R with H2O doing the work. So let me bring up my presentation. Thanks for everybody coming tonight. As I was driving here to warm and sunny Las Vegas tonight,
You're 3 days late.
this is the picture from the parking lot as I parked here.
So we can blame you?
Yeah, not what I was expecting. This is my iPhone didn't photograph it, but very well. But this is the mountain to the west. Not what I was expecting, right? And so one of the things that sort of struck me as a parallel is, and what I wanted to bring from that shot before, where the CPU cluster was active on the right, is you're probably not, most people that are R users aren't expecting to do really scalable things with R. And so one of the things that I want to do with H2O, or tell you about H2O, is to motivate how to think about addressing scalable problems and using R with big data. Millions of rows, billions of rows, right? We can do billions of rows, process billions of rows in seconds using H2O and drive it from R. And that kind of really might challenge your thought, your expectation, or your mental model of what you can do with R. Kind of like snow on the mountain in Las Vegas kind of messed up my image of Vegas forever.
You didn't find it, you were here on Friday. What was it, 75 on Friday?
So here's a little outline of what I'm going to do, but I think it'll be very driven by what you guys, how you guys steer me towards what you're interested in. And, but this is kind of my plan. I'm going to talk a little about H2O, the company, a little about H2O, the software, how we scale R using H2O as a backend, and then do some demos and maybe talk a little bit about how we actually distribute some stuff. So I'm going to show you a little about how we use it, or how you can run big data on H2O, and then I'll talk a little about how it really works, because people often find that interesting. And Q&A, we can do Q&A at the end, but we can do it all throughout. Just any questions, fire away. So let me start by talking about the company. The team's about 30 folks right now. We're based in Mountain View, California, so Silicon Valley. The company really got going sort of at the beginning of 2012, I would say, in terms of developing code and working on H2O. The 2 co-founders are Sri and Cliff. Sri, his dad actually is a mathematician, and so he a lot of the drive behind the company, or behind what the company works on is sort of, that was the genesis in many ways, is his interest in math that he sort of got growing up. Cliff actually was the other co-founder of the company. He worked on Sun's hotspot. So if people are familiar with the Java virtual machine, he's kind of the guy that invented the Java virtual machine being fast. So the hotspot compiler, which is a just-in-time compiler inside the JVM, which translates bytecodes into machine code sort of seamlessly so that you don't have to see it, it just programs run faster. He worked on that. Myself, I'm really a computer person. My background is hardware and software, very classical computer science, computer engineering kind of background. And so I actually am a fairly new person to the world of data, big data, analytics, and that sort of stuff. So for those of you that are just trying to get going, you persevere and you can do it. Here is the picture of the team, a number of members of the team. These are the folks that make things happen. And one of the things that I'll mention about our team is it's a nice mix between computer folks and math and the analytical folks, because on the computer side, people with the computer background or the engineering background, the systems engineering background, they're good at building stuff and delivering software. And the people with the math background are good at coming up with how to what algorithms to build and how to use them. And so this blend at the company, I think, is a good one for developing this sort of thing. In terms of the people in academia behind the company, these three gentlemen are very well known in their respective fields. Our advisory council is the two gentlemen on the right, Rob Tibshirani and Trevor Hasty, very, very well regarded in the statistics field. And then Stephen Boyd, over here, he invented ADMM, or one of his grad students perhaps, I don't know exactly who invented it, but he's the driving force behind ADMM, which we use in our GLM solver, which I can talk about a little later in the presentation. And then the Tibshirani and Hasty are actually, if anybody's seen or read Elements of Statistical Learning, or now, just in the last year, a brand new book came out called Introduction to Statistical Learning, which is great. If anybody is looking for a kind of a very fundamental text to start learning about this topic, Introduction to Statistical Learning. I know that these, the two guys, Hasty and Tibshirani, I believe they are teaching a Coursera course.
Yeah, we're teaching a MOOC, but I'm overseeing the course for doing with Stanford last year. You're the same course.
Whatever.
But actually, at the last meetup that I spoke at, somebody said they were taking the course.
Yeah, I took it last year.
By these guys. Yeah, so having these guys, supporting us, it's really good, right? Because when we have questions, we go say, does this seem legitimate, or are we doing something not quite right? Because one of the challenges we have, the math in H2O isn't really new. I mean, most of it's not so new. Things like GLM, from the 60s, maybe 70s, random forest, 70s and 80s. I mean, maybe even, but the math, it's not really new math. What's new is trying to distribute it and scale it and make it run fast on lots and lots of data. And so that's why it's good to have these guys to, kick off throw an idea off the wall and say, hey, we want to distribute it and we want to take this shortcut. Do you think is that legit or not? And having the opportunity to kick ideas off these guys is great. So H2O, let's talk a little about H2O, the software. It's a platform for building algorithms. It's an open source platform, I should say. The license is Apache v2, which is a very nice and liberal license. You can basically do anything you want. It's parallelized and distributed. It's pure Java. We've written everything from scratch in Java, and that makes it really portable. So you can run it pretty much anywhere, and that's what we do. You can run H2O on your laptop. You know, I'll be doing quite a bit of that today. You can run H2O in your data center. You know, I showed you a cluster. You can run it in EC2. You can run it in a Hadoop cluster. You can run it on, you know, pretty much anywhere. We've tried to make that part really easy. And on top of the sort of platform, we've also provided these models built in, or these algorithms to build models built in. I'll get into that more on a future slide, but just sort of keep in your mind that we've got this base platform. It's open source. You can add to it if you want, because it's all open, and we'd love to have people try to you know, add things. Using the APIs. So we've got APIs at a bunch of different layers. The lowest layer is the Java layer, because all the core stuff is written in Java. You can actually write stuff in Scala as well, if you want. Scala is another JVM language, and so Java and Scala go quite well together. And then we've got our REST API. So the way that many, many languages, including R, talk to the H2O core, or maybe I'll say cluster is maybe a more common word. The way that an R program would talk to the H2O cluster is through a REST API, which just means it's using HTTP and JSON, JavaScript object notation over HTTP to send commands to the back end, the H2O cluster, which will then do some work and give a response back. And so using that model, pretty much anything that can talk to the web is able to interface with H2O. We just literally this week announced a Python client. So if people are interested in Python, you can give that a try too. We've got you know, Tableau, or you know, anything that speaks REST API, which is pretty much any language, can drive H2O. But there are some tricks to doing it, and I'll show you. I'll share some of those tricks that we use for R in a future slide. And then, you know, the last kind of thing about what is H2O, well, it's something that should work on big data and build better models at the same time. So what we want to do is to not have to make you compromise. If you want to use big data, if you want to use all of your data, not sample down, because you don't want to wait for days to finish your calculations, we want to enable that by giving you a platform that scales out. If you are willing to add compute nodes, then something like GLM will scale very well. So big data, better models, yeah, both. People want them both now. So let's get into the algorithms. So in terms of the algorithms that we support, they really fall into two categories: supervised and unsupervised learners. Since you guys are in our group, I wouldn't be surprised if you're familiar with these ideas. Supervised learners just mean that in the data set that you're using to train your model, you know one of the columns is an answer column. You know the answer ahead of time for each row, and that's what you're using to train your model. Whereas unsupervised learners, you don't have an answer column. So in the supervised learning category, we've got a number of algorithms. The one that I'll probably talk about the most today is generalized linear model, which is supporting both binomial classification as well as regression. Binomial classification is for problems that have a yes or no kind of an answer. If you want to build a model, you want to ask that model a question and it can give you a yes or a no answer. Then binomial classification, or another word for it is logistic regression in the GLM space, is a good model for you. Another modeling technique that we can do with our GLM is just plain regression, where if you're, instead of making a yes or no prediction, you want to predict a real number. Say, for example, I want to predict the age of a person based on a bunch of their characteristics. That would be a regression model. But that's only the first algorithm that we support. We also have things like random forest, gradient boosted machine, deep learning. This is extremely popular now in both science and industry. People are really, really getting hot to deep learning. Random forest and GBM, those are both tree models. Have people, just out of curiosity, has anybody heard of these guys in the audience? Yeah? Okay, great. So our random forests, we actually have two implementations. One is a very scalable implementation, and one is a fast implementation where it goes and cheats by copying the data everywhere to try to build the trees as parallel as possible. But GBM, gradient boosted machine, is very interesting because parallelizing that is hard, right? If people are familiar with how the algorithm works, you build a tree and then you build another tree and another one, and they all have to be in series because subsequent trees are built based on the residuals of the prefix that was built before. So you're kind of limited into how much parallelism inherently you can get. And so one of the cool things about H2O is we figured out how to build histograms parallelly and concurrently across a cluster in order to speed up GBM substantially from, for example, a standard RGBM. So all of these algorithms, what we've done, we've made them parallel and distribute across the cluster. And one of the big challenges is figuring out how to do that without violating the integrity of the map. In terms of unsupervised learners, we've got k-means, which is a clustering algorithm, pretty common clustering algorithm. Most people have probably been familiarized with that. Principal components analysis, which is great for dimensionality reduction, and anomaly detection through the autoencoder, which is available as part of deep learning, actually. And so this is kind of a picture of how things really fall together. So here, at the bottom, there are data sources, and as H2O, without data, you can't do anything, right? So getting data in, and what does that data look like is really crucial. We treat data, or I should say, we ingest data and model it internally as a 2D table. So we've got rows and columns. Everything's one big giant table, and we basically read in a giant data frame. You can think of it as a big distributed data frame in the H2O cluster. So where you would do like a read.csv in R, in H2O, you can say H2O.import file. You can point it to a CSV, or a tab separated file, or a Hive, a Hive file sitting in HDFS, a bunch of different formats of that sort. And H2O will be able to read it in. So one of the other algorithms that I didn't mention, because it's not really a machine learning algorithm, it's more of a computer science algorithm, is parse. So we spent a huge amount of effort just on parse, being able to parse data files in a distributed, parallel, fast way, fast and efficient way. And I'll show an example of that, which hopefully will give you an idea of the power of that. But starting from data, what we've done in terms of how we actually built H2O, I talked a little about the algorithms. You can see those over here. That's kind of one big component of what we do. But the way we actually make those algorithms efficient is by providing this combination of in-memory columnar compression and this distributed compute engine built on top of what we've created internally in pure Java as our own MapReduce layer. Not Hadoop MapReduce, but H2O MapReduce, which they're very, very different.
Well,
yeah, quick question.
Yeah, I was wondering whether, you listed there a NoSQL
would that apply to NoSQL databases just like MongoDB that store the data in key value pairs, or others that store in column-based formats?
Well, yeah. So we read in data in we want to deal with structured data. So you know, what we do very, very well right now is to read CSV style things, or tab separated value, or if you're used to using Hadoop, you might have done a Hive query where it creates a directory filled with part files, which basically have, they're basically just a bunch of CSV files. So in terms of what are, you know, the NoSQL thing is more roadmap-ish actually than actual today. What we need to do in order for H2O to read the data is to actually get it into a form where it's a structured columnar kind of a form and read it in. Things that are on the roadmap in terms of data sources are like a JDBC driver. You know, you can think of doing a big select as a very standard columnar way of dealing with data. You know, Avro, Parquet, these sorts of things are roadmap items for us.
I have another question.
Yeah.
S3 up there.
Yeah.
Amazon's S3 is what you're referring to, right?
That is correct. Yeah.
Okay, I think of that more of a file system as opposed to.
It is. It is.
Okay.
But
So
if you can
it
imagine,
knows how to talk to the file system as well.
right? You can imagine having CSV files sitting in S3 or CSV files sitting in HDFS,
Okay.
and we can point to those and read them. And in fact, you can do that from R, which is kind of neat. So, you know, imagine reading a 10 gigabyte file from R. It's hard to imagine, right? But if you have R telling the cluster how to, you know, what to do, and the cluster doing the work, it's not so far-fetched. And I'll show you an example of it happening, actually. So, one more thing I want to mention about memory management. We didn't really talk about this too much, but I think it's worth another few moments. We do a very, very optimized columnar compression. And I've got some pictures of this later in the talk that I'll show you guys if you're interested. It's more about how it actually gets done, what's happening under the hood. But basically, if you think about individual columns of data, they often have values that are very similar. Right? They're very repetitive in lots of cases. And so what we do is we compress data on a per column basis and store it in memory. And for that matter, I should say more about in memory. What we do is we read data into memory once and then run the algorithms, iterative algorithms for machine learning with the data from memory. And this is where H2O's MapReduce is very, very different from Hadoop MapReduce. For those of you that are familiar with Hadoop, the Hadoop world, the center of the universe is HDFS. Right? Every iteration of an algorithm, you've got to go back to HDFS, read some stuff, do a little compute, and then store the answer back to HDFS. So it's I/O, lots and lots of I/O, a little bit of compute, lots and lots of I/O. And the I/O is what makes that kind of an infrastructure slow for doing machine learning. And so now, with an architecture like H2O, what we've done is we've paid that I/O price once by reading data into memory once. And then once the data is sitting in memory in a very, very finely tuned column compressed store, now the machine learning algorithms, the iterative machine learning algorithms that may want to make many, many passes over the data can run very, very fast. So you're trying to leave I/O behind and focus on the CPU and the memory work, right?
So do I need a massive amount of memory then to run this?
So the question is, do you need a massive amount of memory to run this? And the answer is you need enough memory to match your data, right? So if you've got, you know, a small little data file, I can run it on my laptop. And by small little data file, I mean even a gigabyte of data will or more. You know, my laptop has 16 gigs of memory. Even, you know, several gigabytes of data will run fine on my laptop. But if you want terabytes of data, then you need a lot of memory. Yeah. And so this is one of those things where the compression can help you, because if you've got lots and lots of zeros, or if your data is sparse, or if your data is if the columns are very, very similar, you know, if each subsequent row in the column, if they all look kind of similar, or if it's a yes/no column and you've got lots of zeros and lots of ones, we can take advantage of that to potentially reduce the in-memory footprint. So it depends on your data. Is the answer.
And just out of curiosity, have you, with all those hardware guys, have you made it so that you can have a flash disk or a drive or whatever to facilitate bouncing on something where you're dealing with too much data compared to the memory that you do have?
Well, even if you've got flash, you know, it's going to be orders of magnitude slower than
Real memory.
Than memory, right? So what I tell people is to get the experience that you want from an in-memory, a highly optimized in-memory, you know, machine learning solution like H2O, is make sure you've got enough memory. If you're trying to, you know, in the computer science world we call it spill to disk, right? If you're spilling to disk, that's sort of like swapping, right? And
Exactly.
yeah, it's exactly like it is swapping.
Right.
And if you're swapping, you know, that's not what you want to be doing. Is really the answer.
Thrashing.
Did I answer the question?
Yeah. So
Yeah, at least the implication perhaps is that you want to perhaps doing this on a cluster of computers?
Oh yeah, absolutely.
Definitely.
Absolutely. I mean, you don't have to. It's an option, right? If you want to use your laptop on a smaller data set size, and one of the things that's really nice about the way that we interface with R, as I'll get into, you can experiment, or you can work out your workflow on your laptop with a small piece of data, and then when you're ready to work with a cluster, you can just flip the IP and the port that you're working with, right? So you can start off, you know, when I show you H2O and R, you know, basically there's an H2O.init call with an IP and a port. And if you start working on your laptop, you know, point to localhost and work locally with a small piece of data, work out your scripts, get your workflow to where you're happy with it. And then when you've got, you know, time on your cluster, you flip the IP to like one of those big clusters that I showed you when we first got started right here. Now this guy over here, instead of, this is not a laptop anymore, right? I can easily point to the same R script with H2O powering you know, the back end with a cluster of H2O instead of just an instance of one on my laptop. And now here, instead of having say 8 cores and 16 gigs of RAM, which is, you know, a pretty powerful laptop, but still it's limited in what it can do. Here I've got a terabyte of RAM and 128 cores, right? And all I've got to do is flip my IP address, but otherwise the environment feels the same. And that's one of the nice things about working with H2O is it's easy to flip to a big data environment kind of seamlessly.
So how much RAM do you have on those machines?
A terabyte. Each one of them's got 256 gigs of RAM.
Okay.
And actually, you know, depending on what your background is or where you're coming from, that might sound like a lot. But I mean, this whole cluster here probably costs, you know, if you were to buy it today, it would be maybe $30,000 or something. It's not really that
But you
much
would just
money.
buy time off of Amazon anyway, so you would be paying that.
Yeah, you can buy time off of Amazon. That's certainly an option. If you're going to use it all the time, it is actually probably cheaper to just buy the cluster. The Amazon machines are definitely usable though, and they're super convenient. I mean, it's a heck of a lot easier to fire up 16 Amazon machines than to order.
I mean, a lot of times when I do
rack them.
it's just, I throw it at it, and I just want to know that one thing. Once I have
Yeah.
the algorithm, then I can go ahead and implement it, right?
Yeah,
Sure,
yeah.
that'd be a company itself.
So it'd be a whole lot cheaper to just, I mean, I'm not doing what you're doing where you're running it all the time, so.
Yeah, it's Amazon. It's a nice flexible thing, and we work with all of them. We work with Amazon. We work with Google Compute Engine. We work with the Microsoft Azure. one of the nice things about just being a Java program is we'll run anywhere if we don't care. Okay. So let me go back to the presentation. Okay. So I've talked about these boxes, and at the top, I just want to point out the different languages. We support R, we support Python. Those are done through the JSON and REST API, through this API layer here. We've got an interesting, inside of H2O, there's actually an interesting expression evaluation language, which is one of the ways that we make R run fast. So we actually allow you from inside of R to type expressions, and we'll intercept those expressions and actually forward them to the H2O cluster and evaluate them in the cluster. So you can type some R expressions, and on big data like millions or tens of hundreds of millions of rows, and H2O will evaluate that R expression for you. There are limitations, of course, to that. It's not going to do any old thing, right? R has thousands of packages. Most of them are written in C or Fortran, actually. But what we'll do is, so we're not going to take a Fortran package and distribute it, of course. What we do is if you've got base R expressions that you want to use to, for example, build new columns, create interaction, create new terms to build models, interaction terms or that sort of thing, that's a great use for R on H2O. And then the last thing I want to point out about this slide is we've got this scoring engine capability, and this is kind of neat. What we do here is after you've built a model and you like it, you can push a button and you'll get Java code for it. So you can spit out instant model that you can then take and embed in any kind of environment very, very easily. And that Java model that gets spit out doesn't have any software stack requirements. It's got no dependencies. It doesn't even depend on H2O. It's meant to be utterly, stupidly simple, just straight line math. It doesn't do any allocations. There's no GC issues. It's really, really basic stuff. But what's cool about it is it's instant, right? You don't have to do any work of once you figured out, okay, I want this tree model, you don't have to go code it. The code just instantly spits out. So I can remind me to show you an example of that if I forget. It's neat that just looking at the trees, I mean, it looks like tree code in Java. It's exactly what you would expect it to be. Okay, so sorry, my PowerPoint got a little. Okay. So what I'm going to do next is let's talk about how this actually works, and then I want to show you an example. So I've been talking about REST API and talking about data frames and talking about H2O clusters. And here's a picture actually representing what that looks like from the perspective of an R user. So imagine this is your R world over here, just a regular R, GNU R, nothing odd, nothing special. Could be Revolution R, could be any R implementation. We don't really care, it doesn't matter. And over here is your H2O cluster. And between them is network, right? So this is basically the path that we use to have H2O be controlled by your R session. So H2O has a package. In fact, it's just in CRAN. If you do install.packages of H2O from CRAN, you'll get it. And what you get there is basically this front-end stuff, as well as the ability to run R locally on your laptop. Here in this clustered environment, to get this to work, I've got to actually run, pre-run a cluster, which is very easy. It's just running a few Java instances on the right machines, and then I can point my front end to my cluster. And so what we've got here is basically a world where on the front end, you've got your plain old R, you've got the H2O R package, and here, as an R user, I'm telling the back end what to do using this REST API, but it looks like R code. So R is a very interesting language in that you can hook a lot of stuff. You can really intercept a ton of stuff, and we do. So we've got a class, an S3 class, as part of the H2O object, which is basically just an H2O data frame. And so on the front end, you've got this object, this little tiny object in the R runtime, and it's got the IP and the port of the cloud in it, the H2O cluster, and it's got a key name. And by key name, what I mean is it's really just a pointer or a handle to this distributed data frame sitting in the H2O memory, in memory. And so it sort of looks like magic, but really what it does is it lets you, from here, operate on a billion rows as if it were behaving, it's just sitting in your R session. And so that's, from the standpoint of how you would expect to use it, that's really the way. Let me dig in one level deeper. And this is kind of the same principle here on the left and on the right. This left side is your R process, and on the right is H2O, the H2O cluster. And what I've done is I've broken down in a little bit more detail how you would actually call GLM from R on an H2O cluster. And so you can see there's just a standard R process. You run an R script. You call this GLM function that comes as part of the H2O package. And that's doing a REST call over HTTP and TCP. And then on the H2O side, it's actually kicking off the algorithm. And when it's done, it'll send back a little tiny object that sits in R that's a handle to the model information. And so what's interesting about this, and I kind of didn't really think about this until I heard John Chambers, who was one of the fathers of S, actually, at Bell Labs, talk about it. And the way that he described it was R as a language, or its precursor S as a language, they're really glue languages. I mean, they were never really intended to be the implementation vehicle for modeling algorithms, because they're not that fast. They were never really designed to be that fast. They were designed to be friendly and to be very pluggable, and to be really easy for people to add stuff. And you can see that thousands of packages on CRAN are proof of succeeding at that. But the actual heavy lifting for many, many R packages is C or Fortran, right? And so if you think about what we're doing here, it's not that different. We've got this front end, which is basically just letting the user provide commands to the back end. And instead of being written in C or Fortran, we wrote our package in Java. And instead of calling it through a function call, we call it through a TCP socket call over a REST API. But the spirit of it is really the same, actually, in many, many ways. And so I thought it was kind of neat when somebody like John Chambers kind of points these things out. It's a nice it's nice to see that, to feel that you're on the right track. Any questions about these two pictures, this guy and this guy? Because these are really important. This whole front end, back end separation, the H2O package having little tiny objects on the front end that represent big data objects on the back end is super important.
When you're writing this stuff, do you have to think about that as a pointer? Or is the whole thing just kind of hidden behind?
It's hidden, yeah. I'll show you actually. In fact, I'll show you right now an example of this. It's hidden. You can look at it and you can sort of take it apart a little bit, but the idea is not to have to. The idea is to have it be pretty invisible. and not to really have to worry about it. Yeah, so if there are no more questions on these two, I'm going to just dive into.
You could just treat this as its own function and just send the stuff over.
Yeah, I'm going to,
Yeah, let's go
like,
ahead.
literally the very next thing I'm going to do is show you an example. So if there are more questions, I'm happy to take them. Otherwise, let's go to the example.
Is it hard to install?
Super install.package is H2O. That's it. It's the standard.
Other machines. Oh, okay.
So like, the question was, is it hard to install? And so for the single machine case, just literally installing it from R is super duper easy.
Sure.
If you want to run a cluster like this, then you need to make a choice about how you're going to start your cluster. One of the options is I'm going to start it by hand, by running java-jar h2o.jar, which is the standard way of running Java programs, and start the cluster by hand. Another way, and this is very popular, especially in companies, is to have a Hadoop environment. And in a Hadoop environment, what you would normally do is store your data in HDFS, the Hadoop file system, and then we can actually use Hadoop to launch an H2O cluster with, say 5 nodes, and each node has 100 gigabytes of memory, and boom, you get an instant cluster just with a one-line command, the way you would start any Hadoop job. So there are a few different ways to start the clusters, but most of them are
It's just a server running on each one though.
they're all pretty easy. Yeah.
My understanding was that this was really built pretty much for Windows and Mac. Linux is available.
What do you mean?
Well,
That
it's
doesn't
probably a little
sound
bit
bad.
hard to get started with it, from what my understanding was. And I've got it installed on Windows here.
That's not what I would.
I haven't gotten around to installing it on Linux yet.
Well, if it's an R package, it should be easy to install on any OS, right? As long as you.
Yeah, the R package.
R.
The R package will. As an R package, it's easy to install.
I'm
Anyway.
talking about the H2O itself.
So I can show you. I'd be happy to just.
You need Java installed too, right?
You need Java. Yep, absolutely.
Which
But-
version?
The version I would recommend is the most recent version of Java 7.
Well, Java is the
Java 8's fine too. I mean, Java 6, 7, 8. Java 8's kind of the most directed to download now on the Oracle webpage. I would say Java 7, the most recent version of Java 7, is probably the best tested Java. And then I would say there are still lots of people out there on Java 6 because lots of Hadoop environments have that as their default. And sometimes, it can be challenging to get a 1,000-node Hadoop cluster to move forward on something like that, right? It's sometimes easier just to start in the cluster.
Tolerant is what you're saying.
Sorry?
It's tolerant of the version.
Yeah, I mean, we don't have any, we're a pretty standard use of Java. So what I was going to show you is, here I'm going to start H2O on Linux. So literally what I did earlier today is I downloaded, let's see if I have it here. If it's, okay, so I downloaded this guy from our website, and if I bring that up, that looks like this. Here's our website, h2o.ai. If you go to the download page, this is the recommended version I would say you should play with. It's Nother 2.8.4.4. That's also the version that's in CRAN right now. So if you do an install.packages of H2O from CRAN, that's what you'll get. If I click here, it looks like this. And to download H2O, you can download it from CRAN, but you can also download this zip file here, which also has everything you need. And if you were going to run on a Linux machine, you might choose to download this way. I have that right here, and I packed it locally. It's literally just download, unzip, And then if I cd to H2O 2.8.4.4, and I do java-jar H2O.jar, and I'm going to give it a fake name so it doesn't collide with any other clouds, now I've got an H2O cloud. So that was Linux. It's not art. Now, if you want to figure out how do I have many nodes across many machines, then of course there's a little bit more coordination to be done, but it's not bad. I mean, compared to installing other software, it's trickier.
You got it.
Okay, so let me go to this window here, which is my RStudio. And what I'm going to do is just show you a quick example of using H2O on a big data environment. So here, let me start. This is I'm sure everybody's seen RStudio, right? I probably don't need to talk about that. Over here, you'll see that I have the H2O package. I guess my window is not the right size, so I'll skip that part. But basically, what I've got here is an R file. This is in GitHub, actually. It's in our GitHub. And here, what I'm going to do first is just connect to my big data cluster. So here I ran h2o.init, and what that does is give me a handle, h, to my cluster. And now, if I import a file, I can give my cluster a pointer to a file here, home Tom K airlines all.csv. And when I push return there, you're going to see the cluster go to work. And what I should point out is blue, that blue color is idle, actually. So when you see those blue CPUs, they're actually not doing anything. The green means busy in user code. And you might see a slight little bit of red, and the red means busy in kernel code. And so what you saw happen just there is my cluster of 4 machines with 128 cores ingest 120 million rows of a data set that's 12 gigabytes on disk. And that happened in like less time than I can even finish the sentence, right? So scalable is what I would emphasize, right? And the more machines you give it, the more scalable things like parse and things like GLM will be. So the next thing I'm going to do is just in case you didn't believe me, 116 million rows and 31 columns. Here's a head of that data set. I can talk a little about this data set actually. So this data set is from the FAA. It's an airline data set, and each row in this data set represents one flight within the United States. And it's basically 20 years, a complete 20-year history of flight data, every flight in the United States. And the rows are flights, and the columns are features about the flights. And the features that are interesting, especially for modeling, are things like what the carrier was, what the origin airport was, what the destination airport was, things like that. And what I'm trying to do here is build a model that lets us predict, is the next flight going to be delayed? Is my flight home going to be delayed? So to do that, I want to build a test train split. So I pulled in one giant data set, but now in R, I want to build a test train split. So here, I'm going to create, and this is sort of a little H2O-ism, this H2O.RUnif, this random uniform thing. Normally in R, when you call RUnif, it's going to give you just a number. What we want to do here actually is use H2O.RUnif, which gives us a vector of numbers. So every row in that data set now gets a number that lets us make a probability evaluation for that row. And so I'm going to use that number that we just created to do a test train split. I'm going to take 80% of my data for training the model, and then 20% for evaluating the quality of the model. So here I did, I got my 80%. Now I'm going to do my 20%. And you can see as I step through, you see a little burst of activity, and it's pretty fast, right? It's, that was splitting 120 million rows.